All right, thanks for watching. And I was actually in my office thinking a little bit about the Fourier transform, and I realized there's actually a super neat way to derive the product rule of calculus using the Fourier transform. So now today in this video, we're literally gonna kill a fly with a bazooka. So I'm super excited because this is pretty neat. I guess it illustrates how neat the Fourier transform is, but it's cool. So let me remind you, the Fourier transform of f is the integral of this curly thing, f of x e to the minus 2 pi I x xi dx. So you take f, you multiply it by this thing that goes round and round and round, and you integrate it with respect to x, and the only thing that remains is this xi. And for today, there are two facts you need to know. So first of all, if you take the Fourier transform of the derivative, there's just an extra factor that appears. So the good thing is the Fourier transform turns differentiation into multiplication, which makes it really nice. But on the other hand, there's something else. It turns multiplication into convolution, which is not very nice. So the Fourier transform of fg is the convolution of f hat and g hat. And I like to remind you that the convolution of two functions just defined as the integral of sort of the multiplication f of y, g of x minus y dy. And what makes it easy to remember is that the sum of the two has to be x. And maybe another video I will explain, or have explained already, that it's sort of like multiplying polynomials, where you take sums of terms which equal to your coefficient. But okay, and by the way, you may say, objection, Your Honor. Well, this is not a court of law, but you might say, hey, didn't we really use integration by parts to prove this? And doesn't integration by parts rely on the product rule? Yes, it does rely on the product rule, but I think in the end, I will show you that you can get by proving this formula without using integration by parts. So again, if you hold your thoughts, wait till the end, and then your doubts will be solved. Okay, but first let me give you the proof of the product rule, because, so claim, I want to show you that fg prime equals to f prime g plus f g prime. And for this, as I said, let's use the Fourier transform. So here's our proof. Well, let's take the Fourier transform of fg prime. So fg prime of xi hat. By this formula, and remember the Fourier transform, if you take the Fourier transform of the derivative, there's just this extra factor that comes out. 2 pi I xi fg hat of xi, because the function was fg. And now remember also that the Fourier transform of fg becomes a convolution. It's a convolution revolution. So we get 2 pi I xi f hat start with g hat. So f hat convolved with g hat xi. And remember the definition of convolution, that's 2 pi I xi, integral from minus infinity to infinity. I don't want to use xi, let's use another variable, eta. So f of eta, f hat of eta, g hat of xi minus eta, d eta. Very confusing because we added some Greek to it, but remember the sum of those two has to be this variable, so the sum is xi. The question is, how can you write this in terms of f prime and g prime? Here comes a super clever trick. First of all, put this inside, and moreover, decompose this term as follows. 2 pi I xi, that's the same thing as 2 pi I eta plus 2 pi I xi minus eta times f hat of eta g hat of xi minus eta d eta. So all I did, I took this term and then just wrote, instead of writing xi, I wrote eta plus xi minus eta. And notice if you do take the sum of the two, you get xi minus eta plus eta, which is xi. So this is indeed true. And of course, this looks like a foiling party, so let's just FOIL this out. And we get integral from minus infinity to infinity of 2 pi I eta and f hat of eta, g hat of xi minus eta, d eta, plus integral from minus infinity to infinity of f hat of eta, and this term, let's put it with g hat. So 2 pi I xi minus eta, g hat, xi minus eta, d eta. And you see, this is where that plus is coming from. Simply from this little trick of writing xi as eta plus xi minus eta. Because, notice what is happening here. If you take 2 pi I eta and multiply it by f hat, it's just the Fourier transform of f prime. So you're left with integral from minus infinity to infinity of f prime eta g hat xi minus eta plus f of eta, so f hat of eta, and then here it also becomes the same thing. This becomes the Fourier transform of g hat prime. Becomes the Fourier transform of g prime with the argument xi minus eta. And it's precisely because those two things, they have the same argument. That's why we had to separate it into eta and xi minus eta. Okay, that's wonderful. And then what's the next step? So, yes, notice what do we have? We have, you integrate a function with eta and then xi minus eta with respect to eta. The sum is xi. So this is nothing else than as the convolution of f prime hat and g hat. So this is f prime hat convolved with g hat of xi. And same here, the sum of those is xi, and we integrate with respect to eta. So that's the same thing as f hat convolved with g prime hat of xi. Sorry, let me. And the question is, what are all those things? So this is f prime hat convolved with g hat. Okay. And because, the sum of those two becomes, eta plus xi minus eta, that's xi, and you're integrating with respect to eta, so it does become the convolution. And similarly, here you take the convolution of f hat and g prime hat, f hat with g prime hat, xi. And now remember, what does the Fourier transform do? It turns multiplication into convolution. So this is the same thing as f prime g hat plus f g prime hat. And that's the same thing as f prime g plus fg prime hat of xi. Okay, and the question was, what was that equal to? What was the stuff I wrote at the very beginning? Well, it was precisely fg prime hat. And so what do we have? We have that the Fourier transform of f prime g plus fg prime is the Fourier transform of fg prime. And one thing to know about Fourier transforms is if two functions have the same Fourier transform, then they must be the same function. So it's literally you put a, even though you put a hat, you're still the same person. So what we really get is that fg prime is f prime g plus fg prime. So using the Fourier transforms, you've shown the product rule. So how neat is that? But it's, I do recommend the calculus product rule though, because just a little caveat, this one, it just holds if, well, if you can apply the Fourier transform, which usually means, infinitely differentiable functions that are decaying fast to zero. The calculus one, you can apply to any differentiable function. But this is sort of neat, playing with math. All right, if you want to stop here, you can quit the video, but I know some people are just still pissed about that integration by parts formula. And again, to satisfy you, let me show this. So let me show that the Fourier transform of the derivative is 2 pi I xi of the Fourier transform of f. And remember, this is a function that's sort of compact support, that's like 0 at plus or minus infinity. The question is why? And for this, instead of taking limits yet, let's apply difference quotients. So the Fourier transform of f prime, it's something times, e of minus 2 pi I x xi dx. Okay? And f prime, just think of it as f of x plus h minus f of x divided by h. Later we'll take limits because again f is really nice, assume that e is very nice, so everything's nice. Now let's party. So let's expand this out. So that's the same thing as integral from minus infinity to infinity of f of x plus h divided by h e of minus 2 pi I x xi dx. And the other term is just f of x over h e of minus 2 pi I x xi dx. And remember, h is finite, so we're not taking limits yet. So we're taking algebraic expressions that are still nice. And of course, once you see f of x plus h and dx, you kind of want to use a substitution. So u is x plus h. And so we're integral from minus infinity to infinity. F of u over h, e of minus 2 pi I, u minus h xi dx. And du, sorry. Well, du is dx, so we're fine. Minus this term, f of x over h, e of minus 2 pi I, x xi dx. Okay, now take this expression, use another substitution if you want, x equals to u. So, and therefore what I'm saying is you can replace this by anything you want. So just to make it homogeneous like that, let's let it be x. And the nice thing is now, there's this common factor of f of x over h. So it's minus infinity to infinity of f of x. And let's put all the bad derivatives on the e term. So e of minus 2 pi I, x minus h xi, and this dx, minus e of minus 2 pi I, x xi over h dx. Again, totally fine algebraic expressions because we assume, you know, h was finite and everything. Now let's take the limit. So, if you take the limit as h goes to 0 of this, you get the limit as h goes to 0 of this. And as I said, this function perfectly smooth, perfectly nice. Assume f is also perfectly nice and like 0 outside, you know, a finite set. So basically assume that we can just take the limit inside the integral. And again, same here. And what you end up with is the following. So the left-hand side becomes integral from minus infinity to infinity of f prime of x, e of minus 2 pi I x xi dx. And the other side becomes the following. Simply integral from minus infinity to infinity f of x, and so this looks like a derivative, but in the other side, because we're taking minus h, which means there's an extra minus sign that pops out. So if you just take the regular derivative of this with respect to x, you have a minus 2 pi I x xi. But because you're taking x minus h and not x plus h, you have to reverse it. If you want, let h prime be minus h and do this. The point is you have this extra minus sign of e of the 2 pi I x xi, I guess minus dx. And that's nice because, sorry, my bad. You're differentiating with respect to x, so there's no x here. And what you're left with is simply the following. Pretty long appendix, but it's okay. 2 pi I xi, integral from minus infinity to infinity of f of x, e of minus 2 pi I x xi dx. Now, let's just analyze this. This becomes the Fourier transform of f prime. And this becomes 2 pi I xi times the Fourier transform of f. And the question is, when did I use integration by parts? Never. So I just use a substitution. So this is perfectly valid without integration by parts. Hence, my proof of the product rule is perfectly valid. All right, and now hopefully I satisfied everyone. And if you like that and you want to see more cool math, please make sure to subscribe to my channel. Thank you very much.